What's happening, folks? Geologist Philip Prince talking about earthquakes today, but in the U.S. this time. If you look at a U.S. earthquake hazard map, it's going to have a big hot spot on it right here, sort of in the U.S. heartland. There will also be hot spots on the West Coast, no surprise there. A lot of places here in sort of the mountainous West. Get a hot spot there around Charleston, South Carolina. There's one in East Tennessee, one up in New England as well. But that one in the heartland there, that one tends to have all kinds of crazy colors associated with it, showing that kind of right in the middle of it there is major, major, major seismic hazard. In fact, the coloration that you see in the heartland there is actually just like what you see in these West Coast areas, even out there on the California coast, which is a part of the country that we tend to associate with earthquake hazards. So, what's going on in the middle of the country there? Question I get all the time: have you done a New Madrid earthquake video? Done one about the shaking associated with some really huge earthquakes there back in 1811 and 1812, but I haven't talked about why there are earthquakes there yet. And indeed, this heartland spot that I'm talking about is the New Madrid Seismic Zone. It's named for New Madrid, Missouri, a little town on the banks of the Mississippi River. And the last of the really huge earthquakes in 1811 and 1812 occurred just outside of New Madrid. So what's up with this part of the world? It's not on the edge of the continent. There's not like a plate boundary thing going on. It's not mountainous. There's not really a major indicator on the landscape that's obvious to see, at least at first glance, that this would be a place that has a tremendous earthquake hazard. But oh, yes, it's there. And understanding it, or at least understanding what we know about it, requires that you look deep down under the surface. Kind of an interesting way to think about geology, and particularly the geologic history of North America. So first and foremost, where's all this going on? What's up with this place? About all you could see here for a real good reference. Got the Mississippi River snaking along here. We'll highlight it there for just a moment. Going to be talking plenty about it as the video goes on. Little town of New Madrid is sitting kind of like right up there on that big bend. Might not be absolutely perfect with the location there, but it's pretty close. So where are like the fault lines here that cause the earthquake? Well, they're down under the surface, but they would run something like what I'm gonna draw here. I said no, I'm using yellow again, but tends to show up pretty well on the map there. So this again isn't perfect. We need to extend that one out a little bit like that. But they run under the Mississippi River. In fact, in one location here, the fault lines actually cross the Mississippi three times. That's going to pop up momentarily as well. But this gives you an overall sense of just what the layout is. So there's an extensive fault system, and the big earthquakes in 1811 and 1812 were located something like this, and kind of one of the big ones right there, and then you had the last one that was up past New Madrid there. So it was one, two, three, if I remember correctly. And these were, magnitude sevens. That's an estimate, but they did tremendous damage to what was here to be damaged at the time, and they left a whole lot of interesting sort of calling cards in the landscape. And some of those calling cards are actually the most interesting aspects of the event because, among other things, there's a lake right here called Reelfoot Lake that actually formed as a result of these earthquake events. So we'll clear all that stuff out of there and start zooming in a little bit closer here. As you get closer and closer to the land, it looks about the same. Again, like there's places on Earth where big fault lines are really easy to see. They produce a very distinct signature in the landscape. California, what just happened in Myanmar, really good examples there. But in this particular spot, because what's at the land surface is largely pretty young sediment accumulation, or something that's on the verge of being sedimentary rock, but is also not particularly resistant and is rapidly eroding. Like you don't have the background geology that does a really good job of capturing these big breaks in the Earth's crust. But probably the beating heart, I guess, of the whole system here again is this lake, Reelfoot Lake. And when I drew the fault lines in there earlier, you have to go right along the edge of Reelfoot there and come across here because, as you'll see when we get to the diagramming part, uplift here of the land in association with the earthquake, it produced this kind of up and down movement that in effect sort of blocked off flowing water and backed up this area to actually produce the lake there. Now you notice again, fault line there actually cuts across the river, and you can imagine if you're moving the surface of the earth like that and that has to interact with the river, that's going to do some pretty interesting stuff as well, right? So again, all of these features here are, they're sort of ephemeral in the geologic sense, or at least they're not etched into landscape supporting bedrock, again, like you might see in other parts of the world. So what's up with this place? We'll have to zoom way back out here momentarily to try to paint the bigger picture. When you look at this part of the U.S. coming up from the Gulf down here, you got this thing called the Mississippi embayment, and it has this really distinct sort of curve shape up at the northern end of it. New Madrid is pretty close up towards the edge of that, and that embayment is filled in with these younger sediments that sort of obscure the deeper underlying geology, right? So why is this such a tectonic, if you want to call it that, hotspot in terms of structural geology and the actual stress and the movement related to stress that produces earthquakes? Got to do the diagram thing for this one and actually think about what is in the Earth's crust down underneath this location. So we'll hop out to paint here, get it rolling. There's actually going to be two diagrams here. We're going to talk about the overall setup of the crust here, and then actually talk about the movement and how that relates to the river. And then when we come back to Google Earth here and some other maps, some of this story of the Mississippi interacting with that moving ground surface will hopefully make a little bit more sense. So we'll head to paint now. Hang on just a minute. Okay, so what's going on deep under the ground surface here in this New Madrid, Missouri part of the world? Sort of an interesting story here, has overlap with other modern day earthquake settings in the US, but what we're gonna draft out here, gonna keep it pretty simple with this one. Just need big slab here of Earth's crust. Really not worried too much about scale here. We just need a section of material that we can subject right now to some stretching, right? So we're going to pull this thing apart, stretch it out this way, and that, of course, is going to cause it to have to break and sort of thin in the middle to accommodate that stretching. So erase those old outlines there. Like that. There we go. And then we're going to need to give ourselves an area here in the middle that can be stretched and thinned out. Imagine stretching a piece of taffy or something like that. It's going to get longer and thinner in the middle. This is a little more brittle than that, but this would actually go quite deep down into the crust where there would be that kind of taffy-like behavior. We're not going to worry about that in this particular case. Really, all we need to do is show that there is kind of a weak area in the middle of this thing as a result of being stretched, right? So that's kind of a step one there. And if you look at diagrams of this that you find online, typically you do see something that would look like that in cross section, and that's how the Earth's crust responds to being stretched, with all these little black lines here being faults that are breaking through the crust. So when's this happening? I don't even know if there's an agreed upon date here, but it's quite some time ago, 600 million years, something like that. It used to be thought about 700 or so. This is the result of North America's ancestor trying to stretch apart to open up the ancestor Atlantic Ocean that existed before the Appalachians formed. So we're actually going back through what we call two Wilson cycles. So this is the stretching and opening that then collapsed together to make the Appalachians and has then stretched apart to give us the Atlantic today. Suffice it to say, it's really old. The continent didn't break apart here, but it tried to just a little bit, which gave us all these fault lines here that have kind of like broken the crust apart, and the northeast end of that thing is all kinds of complex. We're not going to worry too much about illustrating that either, but this produced a rift system called the Real Foot Rift today, Reelfoot, as in Real Foot Lake. That is a big part of this video, and this is this kind of depression area left from that stretching apart. Do you see this today? No, it's buried under literally miles of sediment. Between the Paleozoic sedimentary rock and the modern sediments, the bottom of the rift is something like, like 5.5 miles maybe or something like that under the ground surface. It is very much out of sight. And for that reason, we're going to erase all those lines showing its surface there, and then we're going to bury this whole area under that massive amount of newer sediment. Okay, so here comes our burial there. Have to clean all these lines up too. I might be able to find a better system for that, but I admit it has not yet occurred to me. That's all right. We're doing okay. All right. We're all out there. Very nice. Okay, so that gives us kind of our modern day landscape with that old bunch of rift faults buried very deeply there. But we have an idea maybe that they're still down there. So we'll have them kind of faintly outlined. But again, you don't really see any evidence of that in terms of the landscape on the surface today, unless you might say that Mississippi embayment up at its north end somehow expresses that. I actually don't know the answer to that question. Right. So got the old faults there. What's happening today in terms of stress? Earth's crust is getting squeezed, kind of like that. Our old faults there are running at an angle to that squeezing, sort of like that. And as it turns out, geology is kind of a game of funny angles in terms of how the crust breaks with respect to stress. Having those faults angled to that stress field sets them up very nicely to slip and produce these really big earthquakes. The fault lines that are producing big new Madrid earthquakes would run something like this, and then kind of step over, and then I think actually I need to take that all the way over basically to the edge of the rift over there. And it should work out pretty well. And as a result of that squeezing, it produces an overall slip here where this side's moving like that, and this side is moving like that. So right here in the middle, as you can imagine, they're butting into each other. And then on the other sides here, you have the strike slip movement. Okay. So what's that going to do? Well, if we were to think about like overall movement, maybe over the really long term here, we allowed this thing to move and slip enough times that we actually accumulated a huge amount of offset. We're going to present a really big, exaggerated version of that. Now, when there's an earthquake, does the land move this much? Absolutely not. I can't figure out another way to illustrate this really other than to show this crazy exaggerated view. But we're going to have to move that side out like that, and we'll work this up in the editor so that you can kind of get a picture of what the overall movement looks like. I might have to move something up there real quick. That's pretty good here. So we'll start to clean this area up. So what we ended up doing here is sort of shifting half of that rift area sort of towards the bottom left of the screen, right? So there has been an overall motion as a result of that stress field acting on those faults. And with that motion right here in middle of the drawing where things are kind of squeezing together, it's actually going to produce a little uplift because with that butting together, that's gonna squeeze things up, right? More on that momentarily, but that area is what the Mississippi comes into and then crosses three times on its way down right there. So I would actually need to extend my third crossing out there just a little bit more. But that area, that big conspicuous bend right there, that's that Kentucky bend in the Mississippi River. Now, in association with this, got Real Foot Lake right there, where the rising land, where the sides are pushing together, produced that relative up and down motion, and it actually kind of blocked drainage there to produce the lake, right? So the big takeaway here is that you have, and we'll make it with big red arrows, you got movement like that on that side, movement like this on this side. It's happening along these deep buried faults there in the Real Foot Rift, and where the faults sort of step over like that, you've got the squeezing there that's uplifting the land. That strand is called the Real Foot Fault, and it produces the Real Foot Scarp, which is one landform feature you can actually go and, I mean, it would actually be like a bump, like a step up in the landscape today, right? So at the end of the day, it all comes down to these ancient buried faults, and you see those represented in a lot of diagrams of this setting. Now, diagram number two, I said I was going to draw two of them here. Wanted to just focus in on like the uplift in the Mississippi River. Hopefully this one will be a little bit easier and faster. Very simple block. We ain't gonna mess with any subsurface structure here. Need a big river though. Yeah, something like that. Mississippi's moving like that. Here's going to be our fault, and it's going to move up like that and actually lift the land surface here. So there's going to be our highly, highly exaggerated uplift of the land, but we want it to be noticeable. Okay, and we're going to do another one right there. And so now you've got this big uplifted area that the river is interacting with, in particular, right on that broken side there. So what's that going to do? Well, water is going to have a hard time flowing uphill there. And again, in real life, not a significant amount of land surface movement, but enough to be noticeable. Not like what is drawn here. This is exaggerated just for the purpose of illustrations. You got a backwater there, kind of a backwater over here, and then in this particular spot, we'll circle it in red there. In that spot, actually going to end up with the river having to kind of like cascade down off of the off of the uplifted area. So if we were to zoom in there, that would be the spot where you would see faster flow or accelerated flow as a result of fault movement. If the event's big enough, like 1811, 1812, with just that one event, you could actually bulge the landscape enough there to see rapids or falls develop sort of right before your eyes. The river would quickly sort of erode that away and smooth itself back out because of the material in the riverbed, just sediment and the physical size of the Mississippi and its drainage. But that's a very simple model right there, but that's what's up with the river getting backed up. It wouldn't really flow backwards per se, but it would be backed up. I've heard a lot of debate about that, about what that actually would have looked like. But yes, it would have absolutely have been disturbed by the bulging of the land associated with that earthquake event, right? So keep that image in mind here. We'll take it back to Google Earth, and then also look at some LiDAR mapping that will give you a sense of what this looks like in the landscape today. So hang on just a minute. Okay, so that's the crustal setup there. You've got this weak spot down underneath literally miles of sediment, and that weak spot is today oriented in such a way that the tectonic stress that is being placed on the crust here is quite favorable to making those old faults move. So you'd have an orientation something like that on your old faults there, and with the stress coming in kind of like that, because geology is this kind of funny game of angles. Those yellow lines there, which would represent some of the older faults down there in the real foot rift system, are just ideally situated to move under that stress field. Now, what else might be going on? The Mississippi River has caused huge amounts of erosion in this area, so there's actually been unloading of the Earth's crust. You would have had an ice sheet coming down pretty close to this not too long back that produced a huge amount of load on the crust. When that went away, caused things to kind of move up and down, and that might also be contributing to the generation of the earthquake events here. But that stress field here is going to be really the big thing that you're going to hear spoken about again and again. So let's zoom back in now and look at those river bends, because probably the most, I guess, outrageous or hard to believe story that you hear about with these big earthquakes in 1811 and 1812 is that they made the Mississippi flow backwards, and it made sort of like rapids, what they call waterfalls. Be interesting to consider just how big the disturbances in the river actually were. But you can imagine, sort of as we drew into the diagram there, you got the fault scarp, the fault lines expression coming across there, this area rising up, this area relatively moving down, that you're going to end up with, sort of this swirling backwater here where the river suddenly has to go uphill, if you will, and then it's really going to be flowing strongly where it has to drop back off of that scarp, and then you're going to have another swirling backwater where the land went up again there. So there actually is truth to the ground surface moving and interacting with the river and producing all of these crazy effects that folks on the river, riverboat captains, for example, would have absolutely witnessed. A lot of the effect on just the background sediments here, when you give a good shake to unconsolidated sediment, it tends to liquefy. So you have this liquefaction process that actually makes sand kind of erupt. It's like saturated sand will erupt out of the ground. They call it a sand blow. Tons of those, and they've actually been studied at length to find out that in this area, it seems you tend to have big earthquakes every 500 or 600 years, and that's been the case for a couple thousand years now. There's not that many intervals of 500 or 600 years within a couple thousand years, so that thought on recurrence interval could probably use a little bit more data, but it's really just a matter of hurry up and wait there. Suffice it to say that given the potential for big events here, all this unconsolidated sediment, the fact that you got a lot of really big cities today very close by to this area, big earthquake events here would be they would be something pretty bad to deal with. Wanted to take a look at LiDAR in this area, and in this case, usually I do a Google Earth overlay, but I want to use the national map here. Got other videos talking about how to load this up, but what we're looking at here is the stretched hillshade in the national map viewer, and it actually shows very clearly right here, this dark line, that is the real foot scarp, and that is in association with the land going up and actually blocking off the water to make real foot lake right there. So you have this relative up down movement that produced the backwater there. And if we clear that out and pan to the north just a little bit, you can also visualize how that scarp system there would end up going across the river and making one, two, three crossings right there. So really, I don't know, really interesting place to have a huge sort of land surface altering earthquake event right underneath a big bend in the river. Is that bend in the river associated with past events? Is that somehow an expression of this? Wouldn't surprise me in the least bit. I don't know that for sure, but it seems like a pretty conspicuous overlap there. So if you take it out again here and think sort of bigger picture. Sometimes it takes the national map here a minute to minute to load up. There we go. The stretched hillshade starts to look kind of crazy when you get too much background topography, and it's really good for looking at something like the meanders of the Mississippi River there. You know, again, you'd have fault coming over, you know, kind of stepping across like that and going up there with the relative movement being like, gotta get it right here. Good gracious. There we go. And that's going to give you kind of the squeezing there that's going to cause that area to uplift there. So again, even with this view, it's not a place that just grabs you and gives you a shake and says, you know, big earthquakes here, look at these features in the landscape. But you can see them, and the reason that they're so kind of mysterious and also dangerous because they're not obvious to see is that it has to do with what's going on in that rock geology, literally many miles beneath the Earth's surface. So in terms of prediction here, there's earthquake activity here all the time. If you actually look at earthquake records in this part of the country, you actually see in terms of just putting a dot where the earthquakes happen, you know, you'll basically see that pattern start to develop kind of along those faults there. So even without like a line drawn, if you just look at where quakes are happening, they do a very nice job of showing you where these moving fault surfaces are located. And if you look at the notorious beach balls for these earthquakes end up looking like this. And you can find this information on a variety of websites. If you were to search for New Madrid focal mechanisms, you're gonna see something like this. And then down in this segment here where the actual like compression's located, you tend to get at least some evidence of that difference. So this would be like a thrust style mechanism there, and then we got this strike slip going on the sides there. So a place that is understood largely by this kind of like proxy evidence, just sort of like watching the little earthquakes that go on down there under the surface. But they're pretty useful for painting a picture of what is ongoing and what would likely be the source of a bigger event in this part of the world. So when you see that big bend there in the Mississippi River, and I guess like one of the spinoffs of this that doesn't necessarily have to do with the earthquakes, I guess, and I didn't even know this until very recently. There's like an island of Kentucky right there. It's like you got like Missouri, Tennessee, Missouri, and you got this one little island of Kentucky right there in the bend, which I guess is why it is actually called the Kentucky Bend. Kind of a little geography trivia there. When you see that bend, it's a good reminder not only of where this kind of thing happens, but also the fact that even in landscapes where the bedrock or mountain topography or something like that isn't just screaming, watch out for this place, there's still plenty of potential for geologic hazard. Will this I don't know, will this come into play within this generation, within our lifetimes? We're a little over 200 years off the last big event. So if assessments are correct of past events, we should have a little bit of time to spare. But you never know, and it's something very interesting to think about in a place that right now, as of today, just had a big tornado event, facing a big flood event now. Also have this other form of natural disaster potential there as well. So just about any landscape, regardless of where it is, has the potential to be pretty dynamic for one reason or another. And just because things like the weather are typically the big story here, you can't sleep on the geology as well. So I hope you found this video interesting and hope you check out the next one when it comes out.